Hello and welcome back to the channel. Today I want to talk to you about something that has bent the minds of philosophers out of shape for many centuries. I want to talk to you specifically about Zeno's paradoxes of motion. So these are ancient puzzles, but they touch on something really quite deep. What does it actually mean to move from one place to another? Zeno lived in ancient Greece around the 5th century BC, and he was a student of Parmenides, who was a philosopher that claimed that change is an illusion. Parmenides and Zeno and so on, they are considered part of the sort of pre-Socratic philosophical movement. So Zeno took Parmenides' idea about change being an illusion, and he tried to prove it with a series of paradoxes that were designed to show that motion itself is impossible, or at least not as straightforward as we think. So let's walk through his four most famous paradoxes one at a time. But before I do that, there are 10 known paradoxes of Zeno. But it's likely that there were around 40, but we only have, through some quite careful reconstruction over the years, we only have access to 10 of them. And in this video, we're only going to be talking about 4 of them because they are specifically the paradoxes of motion. So the first paradox we're going to have a look at and think about is the dichotomy paradox. So let's say that you want to walk across a room. Zeno says that before you get to the other side, you first have to get halfway. But before you can get halfway, you have to get a quarter of the way. And before that, an eighth, a 16th, and so on and so forth. And he points out that there are an infinite number of smaller steps. So if you have to complete an infinite number of tasks just to walk across the room, how can you ever get there? Now this makes it sound like motion is impossible, that you'd never actually finish the steps, you'd never reach the other side of the room. So that's the dichotomy paradox. Now there is a solution to this and the other paradoxes that I'm going to share with you. But that solution wasn't possible until much later on, but we'll get into that. So our next paradox is Achilles and the tortoise. So imagine the great runner Achilles racing a slow-moving tortoise. To give the tortoise a head start, Achilles lets it begin a little ahead. So by the time Achilles reaches the spot where the tortoise started, the tortoise has moved forward a bit. And by the time Achilles reaches that spot, the tortoise has moved forward again, just a little. And this keeps happening. Achilles is always arriving where the tortoise was, but never quite where the tortoise is. So it seems like he can never catch up. Again, Zeno uses this to argue that movement is an illusion. So that's Achilles and the tortoise. And our next paradox is the arrow paradox. So now I want you to picture an arrow flying through the air. At any single moment, if you freeze time, the arrow is just sitting still, occupying a space exactly its own size. It's not moving forward at that instant. But if every moment in time is like that, just a frozen instant where the arrow is motionless, then how is it ever moving at all? It seems like motion disappears when you try to break time down into tiny pieces. So that's the arrow paradox. And our last paradox, the stadium paradox, is a little trickier, but here's the idea. So imagine 3 rows of objects. Let's say 3 lines of people. One row stands still, one row walks left, and one row walks right. Now, if you compare how fast the two moving rows pass each other compared to how fast they pass the stationary row, you'll notice something quite odd. Depending on your perspective, they seem to be moving at different speeds. And Zeno points this out to suggest that our basic understanding of motion might be confused or even contradictory. Okay, so that's the paradoxes. And you've probably got some idea about how we would respond to these paradoxes. So here's the key idea. So Zeno was absolutely right to raise these questions, but he didn't have access to the mathematical tools that were developed centuries later. Once those tools came along, especially through the invention of calculus by Newton and Leibniz, we were finally able to understand what's really going on. So let's take each paradox again and attempt to show how to resolve it. But we're going to do it without needing any maths, because this is a philosophy channel, not a maths channel. And, well, a short video is nowhere near enough to teach calculus. So we're going to do this without the maths. I'm going to try to, anyway. So we're going to start with the first paradox, the dichotomy. So if you remember, the claim was that to get anywhere, you must first get halfway there. But before that, you've got to get a quarter of the way, and so on and so forth, right? So you've got these this infinite number of halfway points where essentially motion seems impossible because you'd never actually get started. So when we think about this, there are infinitely many steps to walk across the room. But, and this is important, not all infinities are equal. So imagine for a moment that each step you take is half as long as the one before it. So while there are infinitely many steps, each one takes less time than the last. Eventually, the total time it takes levels off. You're not stuck doing an endless task, you're just doing a series of quicker and quicker moves. And they do add up to a perfectly reasonable journey. You can get across the room just fine. And you know this to be true because you can physically get up and walk across the room. So if you're watching me on your phone right now, I want you to do that. Go and walk across the room. Did you make it to the other side? Yes, of course you did. So our second paradox was Achilles and the tortoise. So the claim in that paradox was that the runner, Achilles, the fast-footed Achilles, is often put, gives a tortoise a head start in a race. So when Achilles reaches the point where the tortoise started, the tortoise has moved ahead. And by the time Achilles reaches the next point, the tortoise has moved again. Therefore, Achilles can never overtake the tortoise. So it seems that Achilles must complete an infinite number of tasks, catching up to where the tortoise was, to overtake him. And the resolution that we discussed a moment ago for the dichotomy is the same idea here. Achilles does reach the tortoise's previous position over and over, but each time the distance he needs to cover is smaller than the one before. And because he's so much faster, he closes the gap more and more quickly. Even though there are many checkpoints he passes along the way, the total time it takes to overtake the tortoise is actually quite short. There's no contradiction here, just a surprising pattern that our brains don't immediately grasp. Our third paradox was the arrow. So if you remember, the claim in there was that an arrow in flight is, at any single instant, motionless. It occupies a space equal to its own size. But if If it's at rest at every instant, how can it be moving? And so the problem in there is that time seems to be composed of still moments, so motion seems impossible. And the problem with that is thinking that motion has to happen inside of a single moment. But motion isn't something that exists in a single frozen moment. Instead, motion is about how position changes over time. It's a relationship between one moment and the next. So think of a movie. If you pause a single frame, nothing's moving. But when you play the frames together, you see smooth motion. And that's how reality works too. The arrow moves because its position changes across time, not because anything special happens in one isolated instant. So the fourth paradox was the stadium. And the claim in that was that there are three rows of objects. We used, what did I use an example? I used people, didn't I? Rows of people. So you have one row of people stationary, and you have the other two moving past it in opposite directions. And Zeno argues that this creates paradoxical time intervals when comparing movements relative to different rows. So the problem with this is that it creates confusing conclusions about how long motion takes when observed from different reference frames. And this paradox deals with things with how things look depending on where you're standing, your frame of reference. And modern physics tells us that motion is always relative. And that means how fast something seems to move depends on your perspective. Zeno noticed something odd, but as it turns out, it wasn't a contradiction. It's just a preview of what physicists would later explain using concepts like relative velocity and even much later on, Einstein's theory of relativity. So that's the four paradoxes, but what do we make of all of this? Well, Zeno didn't solve these paradoxes, obviously, but he did ask the right questions, and that's what philosophy really is all about. Noticing when something seems off, even if you don't yet have the tools to explain it. So thanks to thinkers like Newton and Leibniz, who developed calculus, and later physicists like Einstein and so on, we now have the tools to show that motion is real and that infinity doesn't always mean impossibility. Zeno's paradoxes remind us that common sense isn't always enough. Sometimes, to understand reality, we have to push ourselves past what feels obvious. So that is an attempted explanation of Zeno's paradoxes of motion without any confusing mathematics. So hopefully that makes sense. So if there's anything in there that didn't make sense, please let me know in the comments, and I will do my best to respond and clear up any sort of confusions and whatnot. And if, as you have got this far, I would like to ask if you could do all the YouTube things, like the video, subscribe to the channel, maybe even leave a comment with your favorite paradox or your favorite question that hasn't yet been answered. So thank you very much for your time and attention. I hope you enjoyed it, and I look forward to seeing you on the next one. So thank you and goodbye.